Right. All right, thank you, Carnegie Mellon, for just this great opportunity to kind of present here. It's been a great conference so far, and Meredith Wells for kind of running this and kind of overall just helping us kind of run through this whole process. But today our project is about evaluating stolen base fielding with player relationships. And so a big thing with this SMT project was kind of the story of this was to find relationships within teammates. And so a big thing of what we wanted to do was kind of do this with defense. And so we'll kind of explain our process and how we did this project. So traditionally, stolen bases are really kind of measured based on one player, and that is the catcher. So that's caught stealing percentage by if they throw a runner out or not. And so one thing that tracking data allows us to do is kind of evaluate how a stolen base is created and not created. So if you look at stolen base percentage, it's only looked at the catcher, and you don't really know how they did that. Maybe they had a good throw, but you don't really know. Maybe they were able to exchange it really quickly. You don't know that really either. And so with this tracking data, allows us to show the relationship between the middle infielder, the pitcher, as well as the catcher. And so we'll go through those a little more in depth in just a little bit. And so I also like to show this example here of Justin Turner trying to steal this base and kind of explain our process here. So you can kind of see the pitcher holding on here. Decent throw up the plate. Catcher makes a really nice throw, but Turner still gets in. And so one thing we want to evaluate here, the catcher would be blamed traditionally in caught stealing percentage. However, that shouldn't really be the case here. He did make a really good throw on target. The fielder kind of cost them a little bit there by not making that tag. And so that's kind of what we want to look at here. Let me click on the screen. And so how do we measure this? So we do have this tracking data from SMT that tracks where the ball is, where the players are, how fast they're moving, how far they are away from the bag. So we need to kind of evaluate this using all these different metrics that we can find using the data. And so that's a big thing we did here. We built a hierarchical model to predict stolen base percentage at different stages. And we'll talk about those different stages in just a second here. And then using those predictions, we can evaluate the contribution of each player at these 4 different stages that we have here.
So like I kind of hinted at, we have these 4 unique stages of defending a stolen base. So first we have sort of the pitch, or we have the pre-play, which is independent of anything that happens between these sort of defensive teammates. This we attribute to almost entirely just the runner based on sort of the runner's speed. We're going to build a model in a bit, but we want to make sure that we are accurately sort of giving credit to defensive teammates for stopping a faster runner and not giving them as much credit for stopping, say, a slower runner. Next up, we want to look at the pitch, which we can judge as sort of the pitcher's impact on this play. We can judge this based on how well they contribute to stopping the steal. We don't really include anything such as sort of like keeping them on base or sort of pickoff attempts, but we look at specifically on the actual steal attempt itself. Next, we're going to look at sort of the catch, and this is going to be from the catcher perspective. This is going to be looking at sort of their footwork and their exchange and really trying to find their impact in stopping things from that. Next, we're going to look at the throw, which is again going to be a catcher impact stage. We're going to look at sort of the quality of their throw, how long it takes them, sort of that arm strength aspect. And then lastly, we're going to include kind of the fielder tagging ability. And so this is really designed to break this up into the 4 stages, where each stage for the most part is designed to be measuring the impact of the individual player. So in terms of modeling, like I said, we have sort of these 4 unique stages. In each of these stages, we look at kind of the difference between the stages as the true impact of a play. So to start, we really tried a bunch of different modeling approaches. We looked at things like non-parametric methods. We looked at sort of tree-based methods, XG boost things. And a consistent thing that we found was our sample size was really limited. We had about 60 plays, and so any tree-based method or anything like that we tried just really tended to overfit things. So we turned back to basics, which gave us some more sort of advantages. We used a logistic regression approach to sort of model the probability at each stage. A nice benefit of using logistic regression is that we also end up with probabilities and not just outcomes. This sort of gives us a nice way to look at things and sort of validate our model where, a 0.6% chance of a successful steal is not the same as sort of a 0.9% chance of a successful steal. And we can really kind of validate these things and look at where we kind of get things wrong or where the model kind of messes up, where things are different than what we're predicting. Then, like I mentioned, the stage process also really sort of benefits and allows us to look at the contributions of individual players. So we can look at the prediction value at each stage and then look at the change of prediction to sort of give an impact to how each player performed in that in-between point. The last thing is that this really emphasizes interpretability. Like I mentioned, you're able to look at sort of the individual impact, you're able to look at kind of the coefficients and how they're impacting this value, and really be able to pick things out in an interpretable sense that, especially for sort of a non-technical audience, things like tree-based methods aren't super interpretable. They might end up with a little bit more accuracy in some cases, but they're not going to be as interpretable and explainable to sort of a coach or a player or anybody that's going to really be using it.
So we built these different models, and then we kind of wanted to explain our results and our process from that. As Jackson mentioned, we really wanted to focus on the probabilities produced. And since we're like kind of deriving the individual impacts of different players, we really care about the probabilities more than the outcomes themselves. In this kind of model, it's okay to be wrong if it makes sense in the context of the problem. So we focused on log loss and bucketing of different probabilities, so we can look at plays where the probability is less than 20% at the point of the catch and make sure everything makes sense in those cases. So here in our graphic, we have the log loss for each stage. This outperforms a baseline model of just like the average at each stage. And as you can see, like when you get to more stages, you gather more information and your model gets more accurate. And then we also used a leave one out cross-validation approach, which means that we fit the model on 59 of the 60 plays. We evaluate on the next one. We do that process for all 60 plays. And this just kind of maximizes the small data set that was available to us. And then we wanted to walk you through an example of this like process in action. So we have a play, and we're going to walk you through it. So as Jackson said, the pre-pitch stage, all we care about is the runner speed. It's independent of the fielders. And as you can see, the probability of a successful steal in this case is 60%. And then, sorry, it's kind of slow. Then we move to the next stage, which is the pitch. So it's low pitch, the time of the play is pretty quick, and the probability of a successful steal drops. So that way we can attribute this impact to the pitcher. So we get credited with .033 outs on the play. And then we get to the next stage, which is the catcher exchange. We include the new exchange time in the model, which actually increases the probability of a successful stolen base, and we can ding the catcher for that. So for his like exchange, his transition, his pop time on this, he gets a minus for the outs. And then, so kind of the last stage is the throw. The catcher makes a very accurate throw. The probability of a successful stolen base goes all the way down to 10%, and the catcher gets credited for almost half an out on the play. And then we have the outcome of the play. So the player is caught stealing. It ends up with so the fielder gets credited with the remaining 10% on that play. And we can translate these. So we have an outs for the presentation, but you can translate this to like a run value for like prior valuation of the players. And then we kind of wanted the benefit of this approach is I know there's like Savant has like a caught stealing over expected model that focuses on catchers. This allows you to actually like credit the different impacts on other fielders. So if the catcher is getting dinged for like outperforming their expectations, we can know that like their pitchers are really quick to the plate, or their fielders are amazing at tagging, or so on. And this just allows you to like evaluate the different players and get all of them information in the stage of the play.
Our team also created an R-Shiny application to really drive home our goal of making this project as accessible and understandable for a non-technical audience as possible, specifically coaches and players. We did this by providing interactive game situations for each of our 4 stages or 4 models, allowing users to fine-tune each of the parameters and see how that affects stolen base probability and the various outs for each of the fielders. This in turn can lead to player development information in which a coach could, say, put in specific parameters for a specific play from their game and evaluate their fielders based on that. For example, let's say a team has an infielder who isn't converting low stolen base probabilities into outs, such as the Turner clip we showed in the first slide. Then you know that the fielder needs to work on, say, tagging drills in the next practice. Also, The Shiny app provides animations and visuals that once again makes it interpretable. We provide where the ball was caught, where it was thrown, how far away the runner is, just to make it more understandable. Next, I'll kind of piggyback off of Jack's example 2 slides ago and show how that actually looks in the Shiny app. So here we have that 4th stage where you see the specific parameters that we chose, the stolen base probability of 11%, and then finally the outs accredited for each of the fielders. Now, to show the interaction you can have with this, let's say that catcher throw wasn't a perfect strike on the first base side and low, perfect throw. Let's say instead it was high. So the infielder has to grab it and then slam the glove down to get the tag. We can see here, if we toggle between, the stolen base probability here goes up, and the catcher loses outs and the infielder gains outs, just because the infielder makes a better play and the catcher makes a worse throw. Finally, the other thing that the app provides is we also have a tab where, where teams can select from a database of plays, in this case the SMT database, and you can visualize the play, see the various probabilities throughout the play, and then finally the outs accredited for each player. Once again, just driving home the point of providing more visuals and more understandability for this project. All right, here's a link for the Shiny app, the GitHub, the LinkedIn's. I just want to thank everyone for listening and for Mellon and Ron once again for putting this together.
Time for a couple questions, so raise your hand and bring the mic around.
Great job. Real quick, I'm curious, in terms of maybe some of the non-fielder related factors, like did you look at maybe if the pitcher's left-handed or, depending on the lead of the first, of the runner, how that might affect the stolen base probability and some of those factors?
As far as the handedness of the pitcher, we do incorporate the lead or the jump of the runner in the first stage model or in the second stage model of the pitch. So that's included if the pitcher is holding on runners better, they will get a plus for that. And we didn't actually include something for regular left-handed, but I'd assume that a left-hander, if he's good at keeping on runners, will keep that runner closer, and then they will therefore get credit for that in the model.
Really nice project. I just had a question. So I don't know if this is accounted in the model or if it'll be valuable, but for example, if the base runner from first base to second base, for example, is not running in a linear fashion, where they're running because I guess sometimes you're not going to get a perfect linear run when you're running due to some other effects or whatever. So was that accounted in for the model or?
So in the model, it's not a complete continuous model, right? So we separate it into that 4 stages.
Yeah.
But we do have there a distance from the base, and that's the only thing accounted for. So I guess we didn't necessarily include that. But I guess, again, I think that's, if they're going in a curved fashion, that's a less efficient way of running, and their distance is therefore going to be larger.
Yeah.
One more question over here.
Hey, I just wanted to say great work, guys. But the question I had was, are you guys planning on, in the future, implementing the rule changes with how many times you can go over to a base, with the pickoffs and everything, or was that something that you considered completely separate from the model?
I would say that we don't really include that. I think that that's sort of inherently factored in on that play, on the actual sort of attempt of you could look at that as sort of being something determining that runner lead size. I mean, if you've already kind of reached your pickoff quota, your runner can take a bit of a larger lead in that sense, so your probability would probably go up in that scenario, if that makes sense.
And I assume you have to, if I was working for a team and I had a stolen base model, I would probably have to retrain it after this year, because I think that those changes are going to impact the system.
Any questions in the other room? I'm going to take that as a no. So let's thank our speakers. And we'll switch over to the next talk.